what if I have a two-dimensional parametric curve, right? So like what if my parametric curve has an x-coordinate that's a function of t and a y-coordinate that's a function of t, so that this curve lives in the xy plane? Then this formula is going to give me the length of that curve, where a and b are the starting values of t. A and b are the starting and ending, starting point and ending point of your parameter t. So, why would we have this crazy formula? Here's a curve. And what I want to do is zoom in really, 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 really close to this two-dimensional curve. I guess that's as far as it zooms. Oh, maybe I just hit the edge of the document. No, I guess that's as far as it zooms now. Okay, well, that's good enough. If I take just a little segment, like between this point and this point, there is some horizontal change along my curve from here to here that I could call delta x. And there's a little vertical change along my curve in the segment delta y. And, you know, I couldn't zoom in very far, so it still looks a little bit curvy along that small curve segment. But the idea of differentiable functions is that if we zoom in really, really close, it should look like a line. So if I take this function, it doesn't look like a line here, but if I zoom in really, 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 really close to a differentiable function, then it eventually does look like a line as long as I zoom in close enough. That's the idea. So now just imagine for a second that we really did zoom in close enough so that that blue part looks like a line segment. Well, then the length of that blue part line segment is going to be the square root of delta x squared plus delta y squared, because of the Pythagorean theorem, saying that's a right triangle. If we zoom in close enough, then the curve should look like a line, and then we can draw this right triangle with a horizontal component and a vertical component, and then the curved segment is the hypotenuse. So that's the square root of delta x squared plus delta y squared, and then our goal then is to add up all of these little line segments. And so we use that capital Greek letter sigma to say we're going to add everything up. You already knew that. You have taken calculus too, so you know what that means. We're going to add up all of the little line segments that look like delta x squared plus delta y squared. And then I'm going to multiply times delta t over delta t. And then I'm going to distribute the delta t in the denominator to the inside of this square root. And whenever I distribute the delta t inside the square root, it's going to make it delta t squared in the denominator. And then the last step to get our formula that we want is to take the limit of all of this. Let's take the limit as the size of these little segments goes to 0. And since t is our parameter, I can set the small change in t to approach 0. And the limit of all of this stuff as delta t approaches 0 is going to be the integral, because we use the integral sign whenever we're adding up a bunch of really, really, really small things in a limit of the square root of lowercase dx squared over dt squared plus dy over dt squared dt. And then a and b are the starting and endpoints of your parameter. And that's it. That's how we kind of derive this formula. If you were wondering where the formula comes from, that's the full story. Questions about that? Makes sense? So now, what if I have an explicitly defined curve in the xy plane? So we're still in 2 dimensions, we still just have x and y. But what if my curve is not like a parametric curve? What if instead I just have a plain old curve where y is a function of x? That's what I mean by explicitly defined. The way we end up with this formula for the length of an explicitly defined curve. Oh man, that's a bad typo. That should be dx right here. The way we get this formula is we start with the formula we just found for the parametric curve. And I'm thinking for a moment. But basically we do this. When we get to the step here, where I multiply by dt over dt, we want to multiply by dx over dx instead. So one thing I could do is start from this point, factor out the dt from the denominator again, so I get something like this. And then multiply by dx over dx. And this is just dt over dt, that's just 1, that's just multiplying by 1. Also, multiplying by dx over dx doesn't change the value of my integral because it's like multiplying by 1. And so those are fine if I want to exchange them. And then we distribute in the dx in the denominator. And the dx in the numerator stays on the outside of the square root. And then the dx over dx is like the number 1, and the number 1 squared is still the number 1. So we end up with this. So if you are given y as a function of x, you can take the derivative of that function with respect to x, square it, add 1, take the square root, and then that's your integrand. And this time, in this formula, a and b, which are the lower bound and upper bound of this integral, that would be the lower bound and upper bound of x then, along the x-axis, for the curve we want to measure. Does that make sense? Yeah? Okay. So one more then, because we care about 3D parametric curves as well. And the curve length formula for a parametric curve in 3D is this. Suppose I have p of t, and it's this vector valued function in 3 dimensions, or this parametric curve in 3 dimensions. And if I say that the velocity function v of t is just the derivative of the position function with respect to the parameter t, you can give it t as time if you want to. So velocity is the derivative with respect to time. Then we could, using our calculus 3 type of notation, say that the length of this curve is the integral of the norm of the velocity function with respect to time. So it's kind of like we're integrating the speed, right? Because the speed is just the norm of the velocity. We're integrating speed over time. What this is kind of telling us is like, on the one hand, it might just look familiar to you if we expand this out a little bit, because this is the derivative of x with respect to t squared plus the derivative of y with respect to t squared plus the derivative of z with respect to t squared dt. Because that's how you take a norm, and I took the derivatives because we're talking about the derivative vector. And that looks the same as what we just saw before with the two-dimensional curve formula. So maybe you just convince yourself that, yeah, the Pythagorean theorem still works in 3 dimensions, and that's how it should work. The other thing that you could think of whenever you see this is think, this is really adding up all of the speed that we see at every instant times little changes in time. Because speed times an interval in time tells me how far I've traveled. And then we take the limit as the delta t goes to 0, and we get the integral of speed times the limit as delta t goes to 0 is going to be lowercase dt, and again that gets us our familiar formula. But this curve length formula is just integrating your speed function with respect to time. Okay, so find the length of this curve. This is going to be an easy, nice example, I think. This is my parametric curve. What is my velocity vector going to be? Yep, it's my velocity. Okay, so now I need the speed. What is my speed function? Yep. 1 squared is 1, so we just write plus 1 here. And before I go ahead and write the big integral, is there anything I can do to simplify this? Sine squared plus cosine squared is 1, so this is the square root of 1 plus 1. Yeah. So the speed is just a constant. It's the constant square root of 2. And when I find the length of this curve, right, the length is the integral from a to b of the speed my lower bound and upper bound are given to me in the problem. Lower bound 0, upper bound 2 pi for my parameter t. And I'm just taking the antiderivative of the square root of 2, which is what? Yeah. And since I'm taking the antiderivative with respect to t, we're going to call that square root of 2 times t. And for t, we're going to plug in 2 pi, and then we're going to plug in 0, and we're going to subtract those. And so I'm going to get 2 pi square root 2, or 2 square root 2 pi. I guess it depends on how you want to write it. 2 times square root of 2 times pi. That is the curve length. So cosine t, sine t, we've plotted this before in GeoGebra. It just makes a helix. It's like circular in the x and y directions, and then in the z direction it just increases with t. So we're talking about a helix. If the z coordinate was just 0 and it stayed in the xy plane, then the curve length from 0 to 2 pi would just be 2 pi. Yeah, because it's a unit circle. The hypothetical question I'm asking is like, what if that's not t? What if that's just 0? Well, then that makes a unit circle, and so you just have 2 pi. But since my curve is not just laying in the xy plane, but I've also stretched it out a little bit in the z direction, now we've got this 2 times square root of 2 times pi. And so I've got like 41% more curve length because I'm stretching it out in the vertical direction. Okay, that's the easiest problem you're going to see for curve length. They only get harder from here. The reason this was so easy is because it gave me a constant for the speed, and constants are really easy to take an antiderivative for. But any other curve length problem you see is either going to be that one or it's going to be harder than that one. So, new definition. The curvature is given by a capital K. And sometimes I've seen in textbooks, instead of using a capital K, they'll use a Greek letter kappa, but it doesn't look very different. And so I'm just fine with using a capital K, because you know what a kappa looks like? That's what kappa looks like. That's what a capital K looks like. This is what a capital kappa looks like. But like, it doesn't matter to me. So, here's the formula for curvature. This is the definition of what curvature is. Curvature is the derivative of the unit tangent vector, and then you take the norm of the derivative of the unit tangent vector, and then you're going to divide by the norm of the velocity vector, so you're dividing by the speed. And curvature is supposed to be telling us how curvy a curve is. If you have a really high curvature, it means like you've got a really sharp turn. If you've got a really low curvature, it means that your curve is practically straight. If your curvature is 0, then your curve is just a line. It's not actually a curve. So remember, the capital T unit tangent vector always has a norm of 1. It never changes size. So when we talk about the derivative of the unit tangent vector, that derivative is not telling us anything about how the size of the vector is changing. It's only telling us about how the direction of the vector is changing. So in the numerator, that's telling me how quickly, with respect to time, is my curve changing direction. Then what I do is I divide in the denominator by the speed, because if you're moving really quickly along a path, then you're going to be changing your direction more quickly with respect to time. So to get rid of that sort of speed bias, because we don't care about how quickly we're transversing the path through space, we only care about the shape of the path in space, we divide by the speed. And so you get more of an unbiased representation of how quickly the curve is changing direction. That only depends on the shape of the curve. That said, this takes a long time to calculate, and this is a lot faster to calculate. So we're going to use the shortcut formula anytime we have to do a calculation. And you might wonder how these are related and how to prove that this formula is really the same as the formula above this. And if it were me, I'm sort of thinking about how the definition of the principal unit normal vector is t prime divided by the norm of t prime. And so when I see that capital T prime in the numerator, that's the same thing as t prime times n. No, I messed that up. It should be like this. There we go. And last time we also proved a definition for the normal component of acceleration. And the normal component of acceleration was, I think it was something like this. I can't remember that off the top of my head. I don't know if that's right or not. But I can remember what we did to prove that. We said acceleration is just the derivative of velocity. And velocity is just the speed times the unit tangent vector, because that's the direction that we're traveling in for velocity. And so if I want the derivative of this product, I can use the derivative product rule, and I get the derivative of speed with respect to time times t plus the speed times the derivative of t with respect to time. Oh yeah, and there it is. So that's the tangential component, and then the normal component was the speed times capital T norm times n. Okay, and that's the normal component. Very good. So I did remember it right. I just had to jog my memory a little bit. So we haven't gotten to the proof we want to yet. I'm just kind of, getting all the tools out of the toolbox over here in the margin so that I can eventually decide what I'm going to use in this proof. And, we're almost there. Because the definition of curvature, the first formula above, is the capital T prime norm over the speed. And I can rearrange this formula to solve for, no I can't. I kind of can. I kind of can. Let me see this. So let me take this normal component of acceleration and then take the norm of it, and it would just be the speed times that. And then I've got this. Okay. Now I feel better. Where I have the capital T prime norm, I'm going to replace that with the normal component of acceleration, norm, divided by the speed squared. Let me take a pause for a minute and make sure everybody's still on the same page with me. Do you understand what's happening?
Does the n go away because it's a unit vector? Is this on when you took the norm of the component of acceleration?
Yes, you are absolutely right. And thank you for pointing this out, Carter. The capital N is a unit vector. And so if I want to take the norm of this normal component of acceleration, then taking the norm of a unit vector is just 1. Multiplying by 1 doesn't do anything. And so that's why I neglected to write the norm of capital N here, is because it was just going to be 1 anyways. Yeah. Okay. So let me take another look at where we're trying to go with this formula for curvature. I also see V cross A, the norm of V cross A. Let's think about that for a moment and see where we go. I know that the norm of V cross A is the norm of A times the norm of V times the sine of theta, where theta is the angle between V and A. Now we need to draw us a picture that has my vector V and my vector A pictured. Here's my angle theta. And A has 2 components. It has a tangential component in the direction of the velocity plus a normal component that's orthogonal to the velocity. So I can draw this right triangle here. And that means sine of theta is going to be the opposite divided by hypotenuse. And the opposite side of this right triangle is going to be the norm of the normal component of acceleration. And the hypotenuse of this right triangle is going to be the norm of the acceleration vector. So then, let's revisit my V cross A norm. And I'll write A norm times V norm. And instead of sine of theta, I'm going to write this. I'm going to write the normal component of acceleration divided by the norm of the acceleration. Like that. Ooh, and I see stuff canceling. Seeing stuff cancel is always a good sign as you work through these. So I've got the norm of V times the normal component of acceleration. That is the same as the cross product between the velocity and the acceleration. It's kind of interesting. Okay, I'm feeling good about this. I feel like we are a lot closer to our answer. Let's take this identity that we just learned and let's scroll up to see if there's a place I can use it here, right? Because what we're trying to prove is that these two formulas are exactly the same thing. So we started with the definition of curvature, and this is what we have in green. And now we want to replace the lowercase a n with a cross product of velocity in A. Okay, so let me just rearrange this one more time and it should be ready to use. We'll write AN, the normal component of acceleration norm, is equal to V cross A norm divided by the speed. Now, not that one, but this one is what we're going to use. We're going to plug this in right here. And now, having done so, I get V cross A norm divided by the speed cubed. And this is the shortcut formula we wanted to find. All right, so this is a little bit messy. If I was trying to publish this, I would definitely type it up and rearrange some things and make it look nice and neat. But you know, the lesson here that we can take away is if you've got a really hard proof problem, don't stare at it, you know. Start writing some stuff down. Write down relevant things that you know and start to look to see where the pieces fit together. It's like solving a puzzle. You know, my 2-year-old loves jigsaw puzzles. She gets really frustrated really easily, but this reminds me a lot of her little jigsaw puzzles. They're like 6 pieces, and you know, sometimes I have to tell her, okay, that's the right piece, it's the right place, just rotate it, rotate it, rotate it, and she gets mad and she throws everything everywhere. But my point is, if you're working on homework or preparing for a test or something like that, don't get mad and throw things everywhere. I want you to just start writing things down. Write down what you know, and maybe you can start to see where these pieces rotate and fit together. Because whenever I saw this, I was like, oh crap, I did not rehearse this at all before lecture today. I don't know what I'm going to need or where to start from for this proof. And so I just started writing random stuff. Like I started writing capital N equals T prime over norm of T prime. And I don't know if we ever used that. Maybe we did. But it turns out maybe the first thing I needed to write down was this definition of the normal component of acceleration, that formula. And of course I had forgotten that one, and so I have to remind myself what that is. That happens to me all the time. I don't know if that happens to you, but like on a math test, you forget something that you absolutely needed to know, so you sit there for a few minutes to try to work through it, figure it out. So finally we realized what we needed, and then we took the norm of both sides, and then we rearranged it so that we could use it over here. And we started with my definition of curvature, but then replaced the T prime norm with this that we got from that. Then that wasn't quite there, right? That wasn't my shortcut formula right away. What I want to show is right there, the V cross A stuff. So I wrote down, well, what is V cross A? What do I know about the cross product? Well, I know that has to be true about the cross product. And I've got some angle between vectors. Maybe I should draw a picture of the vectors. And as long as I'm drawing vectors with an angle between them, let me make it a right triangle, because right triangles free up stuff for us to use, like trig functions and Pythagorean theorem sometimes help or whatever. And so then I thought to maybe draw a picture. And I figured, well, I care about sine of theta. What is sine of theta in this triangle? Maybe I can use that to replace the sine. Like I said, if you get something that cancels out in the course of trying to come up with a proof, that's like really encouraging. It's a hint that you're going in the right direction. And then that was it. Because the thing I needed to get rid of now is this normal component of acceleration, and using that formula we could get rid of the normal component of acceleration, and that happened to be exactly what we wanted. Question?
When you were doing the sine of theta, how did you get the norm of A as your hypotenuse?
Oh, good question. So this right here is the acceleration vector. When I was drawing my picture to begin with, I said the longer vector that's more horizontal is the velocity vector, v. And this vector over here is the a vector, the acceleration vector. So the length of this vector is the norm, and the opposite side is not the vector normal component of acceleration, but it's the norm of it. And this side of the triangle would be the norm of the tangential component. Because if I don't put the little norm around the symbol A, then I'm talking about a vector. But if I put the norm around it, I'm talking about the length or the magnitude of the vector. And so yeah, the hypotenuse would be the length of the vector A. That's a good question. Are there other questions? Okay. Find the curvature of a circle with radius r centered at the origin. So I'm going to write down my curvature formula. I'm going to write down the shortcut formula because I know it's going to be easier to do calculations with the shortcut formula. And I need the velocity, I need the acceleration, and heck, I even need just a parametric curve to begin with. And so let's talk about what this parametric curve would look like if it's a circle with radius r centered at the origin. That would look like r cosine of t, r sine of t, 0. The z-coordinate equal to 0 puts me in the xy plane. I know that cosine for the x-coordinate and sine for the y-coordinate gives me a circle. And I scale it out by r to give me a circle with radius r. So now, I need the velocity. The velocity is the derivative of the position. So I write negative r sine of t, r cosine of t, 0. And I also need the acceleration. And the acceleration is going to be negative r cosine of t, negative r sine of t, 0. Then I will need the cross product between velocity and acceleration. And the cross product is going to start off with 2 zeros. I don't remember, I definitely told you this during our cross product lecture. I don't know if you remember this from our cross product lecture. But if I've got two-dimensional vectors and I want to take their cross product is a scalar in 2 dimensions. If I've got 3-dimensional vectors, then their cross product is another 3-dimensional vector. But for 2-dimensional vectors, it's just a scalar because the first 2 entries in the cross product end up canceling to 0 because my z-coordinate is 0 both times. So my cross product is going to end up being 0, 0, and then something like VA minus VA. And then it's going to be 1, 2, 2, 1. So the norm of this cross product is just going to be the absolute value of whatever I get in this third entry, which is going to be negative r sine of t for v1 times a2, which is negative r sine of t. And that gives me positive r squared sine squared t minus v2, which is r cosine t times a1, which is negative r cosine t. So I get positive r squared sine squared t plus r squared cosine squared t, and that simplifies to what? just r squared. Because think about factoring out the r squared, and you're left with sine squared plus cosine squared. Sine squared plus cosine squared is 1, and so you just get r squared. So in the numerator, the norm of this cross product is r squared. Now I need the speed for the denominator. So let's think about the speed for a minute. The speed is the norm of the velocity, and that's going to be the square root of negative r sine of t squared plus r cosine of t squared. So somebody tell me, what is my speed?
Is it just R?
Yep. It is just r, because you get positive r squared sine squared t plus r squared cosine squared t. Factor out the r squared, you get r squared times parentheses sine squared plus cosine squared. That's r squared times 1. You get r squared, but that's underneath the square root. So you take the square root of r squared, you get r. Very good. So my speed is r, and that goes here in the denominator, cubed. What is r squared divided by r cubed? 1 over r. So the curvature of a circle with radius r is 1 divided by r. So these are reciprocals of one another. If the radius of the circle gets bigger, the curvature goes down. If the radius of the circle gets smaller, then the curvature goes up. But that's kind of what we expect, right? Smaller circles are curvier than big circles. If the circle gets really big, it looks almost flat. That's why there's flat earthers out there. Right? The equator is just a really, really, really big circle. And so from where we're standing, it looks pretty much flat. And that's the idea. Here's a new definition. The radius of curvature is the radius of a circle with the same curvature as the curve at a given point. And so there's a formula for it, because the radius of curvature is just the reciprocal of the curvature. If you've already calculated the curvature of a curve, you can get the radius of curvature just by taking the reciprocal. Let's find the curvature of this curve and see how bad it is. These problems are normally really, 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 really bad and yucky. It's hard to get excited about this chapter. But, something we just got to do. And I think the answer is, like, in real life, people don't do these by hand. You get a computer to do it for you. But in Calculus 3 class, we don't take our tests with computers. So we have to suffer.
I don't even look. He doesn't like. I don't even know if I made it this far. Like, I don't think he's dumb, but like, I'm saying that he just doesn't. Like,
It's almost like he's incredibly smart because he just watched soccer games every math class we take.
That's what I'm saying.
He does that. He does that.
As long as he gets
mechanics
by,
too.
like-
He just sits in the back and just watches like film. I'm like,
But you're still passing. So
Yeah, he has to be just really smart. I don't get it.
Okay, cross product formula. 2, 3, 1, 2, 3, 3, 2, 3, 1, 1, 3, 1, 2, 2, 1. There we go. So this cross product is going to be 2t times negative 2t, which is negative 4t squared, times minus negative t squared times 2, which is minus a negative t squared times 2. You guys got to check my work. I'm going to make mistakes if you don't. V1 is 2, A3 is negative 2t, so that's 4t. V1 is 2, A2 is 2, minus V2 is 2t, A1 is 0. So the norm of V cross A is the square root of 2t squared is 4t to the fourth, plus 16t squared plus 4. Ah, you're right. Then I need the norm of V, and the norm of V is square root 4 plus 4t squared plus t to the fourth power. Curvature. So this curve does not have the same curvature everywhere like a circle does. The curvature changes depending on where you are along the curve, and we specify where you are along that curve by the parameter value t. And if you know t, then you just plug it in. You can eventually calculate the curvature. So it's kind of yucky. Kind of gross. Math problems that end like this, like, just give me the ick.
When did you learn the term?
It's a good question. Probably from like TV. Just don't know what show I heard that on. So here we go. Find the curvature of the following explicitly defined curve. Well, one way I could define this curve as a parametric curve is I could say, let's make x equal to t. And then y would be t minus 1/4 t squared, and z would be 0. Sorry. And then I can do everything just like I did before. V cross A norm over V norm cube. I see we have just 20 minutes left in class, so I might skip this one. But do you see how I at least transformed it from explicitly defined to a parametric curve? No? Okay. So when I write down just t by itself in the first entry, I'm saying my x-coordinate is just exactly whatever t is, okay? X equals t. So if x is equal to t, I can just say y equals t minus 1/4 t squared, and that's exactly what I did. Set the y-coordinate equal to that. And z is 0, because we're on the plane apparently. Let me see what the last page says. Okay, for a curve in the 2D plane, the circle of curvature is a curve whose radius is the radius of curvature. And it intersects my parametric curve P at a given point and shares a tangent line with P at this point. For such a circle, the center of the circle is called the center of curvature, and it's located at a distance r, remember r is the radius of curvature, away from the point where it intersects with your parametric curve in the direction of the principal unit normal vector. And that sounds like a lot, but let me show you. Let me show you what this is, because that definition sounds crazy if you don't see it. So let's just look at it. That's y equals x squared. What if I have a circle in the plane? That doesn't look like a circle of curvature. Let me fix it. I'm going to give it a radius that I can tweak. Maybe that's a better radius. And then I also want to be able to scoot it up a little bit. And so let me find it, and there it is. A picture is worth 1,000 words, right? For the red curve, this blue curve is the circle of curvature at x equals 0. Because the blue circle intersects with the red curve here. They share the same tangent line, and this circle has a radius of curvature that's equal to the radius of curvature of the red curve. And so the center of this blue circle is what we call the center of curvature for that red curve. I know that's a lot of definitions, but maybe we can find it with pencil and paper here. So my curve was y equals x squared. As a parametric curve, I would write t squared 0, so that my velocity would be 1, 2t, 0, and the acceleration would be 0, 2, 0. Then I would need the cross product of velocity and acceleration. And the cross product of velocity and acceleration is going to be the vector 0, 0, 2. And so the norm of this cross product is going to be 2. And my curvature is going to be that norm divided by the speed cubed. And the speed is the norm of the velocity, so that's going to be the square root of 1 plus 4t squared. So the curvature is 2 divided by square root of 1 plus 4t squared, and t is equal to x whenever I translated it from an explicitly defined curve to a parametric curve. And so I could also write the curvature as 2 divided by 1 plus 4x squared. 2 divided by the square root of 1 plus 4x squared. And when I set x equal to 0,
The velocity norm isn't cubed.
oh, you're right. You're right. Thank you. I got to cube that in the denominator. So I'll write the 3/2 power. So it's cubed and square rooted. That is my curvature. Okay, so where I made that circle was like at the point where x is equal to 0. And if x is equal to 0, this is 2. If the curvature is 2, what is my radius of curvature? 1/2. So you remember my normal component of acceleration is the there's kind of a lot of work, isn't there? I'm trying to find the direction of the principal unit normal vector, but it doesn't have to be the principal unit normal vector. It just has to be the to get a good direction, I just need anything in the normal direction. So it could be the normal component of acceleration, but I don't know if we have enough time. We've got 3 minutes. That's what I'm weighing over. So you can tell that this radius of curvature is 1/2, and that's also the radius of the circle that fits nicely there is 1/2 for the radius. What I was going to try to show you next is the center of the circle is in the direction normal to the tangent. So the tangent is like horizontal here. It's the x-axis is the tangent line, and normal from the tangent would be in this direction, and that's where you go to find the center of your circle of curvature.